Afternoon, students. In this class, we will see about the basics of the Turing machine. The next topic is the Turing machine. Before going to the Turing machine, according to the Chomsky hierarchy, uh, the language, there are different types of languages. That is the regular languages, context-free languages, context-sensitive languages, as well as the recursive enumerable languages. As we discussed, the regular languages are accepted by this finite automata, and the context-free languages are accepted by the stone automata. And the next one is the recursive enumerable languages. These are the languages accepted by the Turing machine. So Turing machine accepts the recursively enumerable languages. That's almost like our normal languages. This Turing machine is the basics for our digital computers. That is the basic computation machine. This Turing machine is the basic computation machine. It was introduced by Alan Turing in the year 1936. And it's a simple mathematical model of the computer, how it works, how the calculations are performed in the computer. That is displayed by the Turing machines. So these are the models that having the computing capability of the computers. The Turing machine can be defined as a finite state machine with an infinite tape and a tape head that can read or write one tape cell and move left or right. It normally accepts the input string or completes its computation by entering a final or acceptance state. If the Turing machine enters the final state, that string must be an acceptable one. As like ordinary machines, the Turing machine model also contains one tape. In the tape only the input symbols are there. That is, what are the things you are going to modify, what are the things you are going to calculate, that is available in the tape only. In general, this regular languages and context-free languages, just we are checking how it is, how the model of the language, as well as how whether the language can be accepted or not. For that one, we are using this finite automata as well as the push-down automata. In finite automata and push-down automata, you can read the contents, but the tape contents cannot be deleted or cannot be changed. But compared to that finite automata, in Turing machine, the tape symbol can also be changed. In that machines, we use only the read head. That is, the content can be read out, but it cannot be changed. But in the Turing machine, you can change the content also. Because it's used for computation. Computation means you can add the values, subtract the values, anything can be possible. So it contains the read-write head. So the basic components of Turing machines are finite control. It contains the set of states, and read-write head. It reads the symbols from the input tape. After reading one symbol, it may go to the next state or it may be stay in the same state. Same manner, the Turing machine can move either right or left. Until now, we are discussing always the strings can be accepted next. This forward move is there for the push-down automata as well as the finite automata. Whereas in the Turing machine, it can move in two directions, right or left. Same manner, the Turing machine contains blank symbols also. That's also considered as the tape symbol. So all the alphabets addition to the blank symbol is considered as the tape symbol. The Turing machine can be defined by using this one, like push-down automata. It can also be defined M equal to Q sigma, tape symbol, delta, Q naught, blank, and final state. For Q is the set of final state, how many states the Turing machine is moving. Sigma is the input or alphabets. Generally, our terminals A, B, 0, 1, all these things are called as the alphabets. And tape symbol means what are the symbols that's available in the tape. And the next transition, the next is a initial state and blank symbol, and the next one is a final state. Initial state may be the final state, or another state can be used for the final state. So here, that is very, very important. Here, all the transitions on in the form of two state and contains left hand side 2 symbols and right hand side 3 symbols. Left hand side contains the state as well as this tape symbol that can be converted to state, tape symbol, as well as move. Either move can be either left move or right move. Two possibilities, left or right. This is the transition function, general form of the transition function, delta of q comma x equal to p comma y comma r slash it. It means after reading this input symbol x is the input symbol. After reading this input symbol x, the state q, this is the state, and this is the symbol in the tape. After performing this operation, the state changes from Q to P. The state changes from Q to P, and this X can be converted into Y. So we are rewriting S with Y, and you may move right or left, anything, right or left. So Q is the current state, X is the current state symbol, and state of change is possible. Without state of change also we can do. These are the things about this Turing machine. So the Turing machine, it can be defined as Q set of states, sigma input symbol, tape symbols, delta is the transition, Q naught is the initial state, P is the blank, and X is the final state. Here all the transitions are in the form of delta of Q comma X equal to P comma Y comma R comma N. Now we will design a small Turing machine for calculating f of x equal to fx plus 1. Our function is f of x equal to x plus 1. I am going to design a small Turing machine for this one, f of x equal to x plus 1. First, you should write, we can write this as, how can you write this one? This can be written as m equal to q comma sigma comma delta comma this one. So, write this one, m equal to, state this one, this is the definition. First, I should write that one. When I am defining this one, m equal to, what are the things? Q, sigma, tape symbol, delta, q naught, then blank symbol, and f. These are the things I am going to identify for f of x equal to x plus 1. If x values are given, then it will calculate x plus 1. For example, if x equal to 1, what is f of x? F of x equal to x plus 1, that is 1 plus 1 equal to 2. F of x equal to 2. X equal to 3, for example, f of x equal to 3. What is f of x? F of x equal to 3 plus 1. 3 plus 1 equal to 4. I'm going to do this one. How the Turing machine transitions must be there for calculating this one. For calculations in the Turing machine, this can be represented in the unary format. For the calculation in the tape. And so this is the tape. Here you give the information in the unary format. That is, x equal to 1 means put 1 0 here. X equal to 2 means put 2 zeros here. X equal to 3 means put 3 zeros here, like that. The input can be given in the unary format. Here I am taking 0 for the representation of the digits. What must be my answer? Or my answer should be, if I am in 3 zeros, x equal to 3 means answer must be f of x equal to 4. I'll get 4 zeros. The input is 3 now, I'll get 4 zeros. What I have done here is 0. I'm keeping this 0 as it is. 3 means it can be converted into 4. Keep this 0 as it is. Keep this 0 as it is. Whatever be the 0, keep the zeros as it is. What I am going to do is, here the blank symbols are there in the Turing machine. Convert the first blank to 0. Okay, because I need one more content, only one more symbol I need. So just convert this blank to 0 and stop the Turing machine. That is, you reach that. When we say the Turing machine is reachable, means if you reach the final state, that's fine. End with the final state. What I'm going to do is read the symbols, move right, right, right. Whenever I face the first blank, convert it into 0 and move right or left and keep it as it is. For that one, first I write the transitions. How can I write the transition? Initially, delta, same like that other finite automatas, Q naught. I'm in the state Q naught. What I have, the first symbol 0. When I read Q naught comma 0, I will write Q naught, same state, no need to go for the next state, or you can go for the next state also. I'll write Q1 comma. Just read the values and move forward. Q1 comma 0 comma R. Then when you read the next 0, Q1 comma 0, then also move forward, same Q1 0 R. Again also in the state Q1, after reading the next 0, I'll write Q1 comma 0 comma R. Whenever I read the first blank, Q1 comma blank, I read the first blank, I'll change the blank into 0 because I need 4 zeros. Change the first blank into 0. So that is, I can change Q2 comma, my first blank is converted into 0 comma R. It means here 0 is keep the 0 as it is. Here also 0 is 0. Whenever you reaches the blank symbol, convert the blank symbol into 0. You should know the concept first. According to the concept, do the things. So these are the transitions required to find the value f of x equal to x plus 1. For this one, these are the transition function. Can you say what is Q? Q equal to, how many states are there? Q0, Q1, Q2. So from our Q is Q0, Q1, comma, Q2. What is sigma? What are the input symbols? Just see here. What are the input symbols? 0 and B. We are processing it 0 and B because that's available here. So our input symbol is 0. Blank is available in the state. Only one input symbol because we are representing the input in only unary format, only 0. Then stack tape symbols. There are two symbols in the tape, 0 and B. So two symbols, 0, B. These two are called the tape symbols. Again, this is delta. And Q0 is Q0, initial state is Q0 only, blank is blank. What is final state? Here the final state is Q2. After processing the strings, it reaches the final state, then that is the acceptable one. We will write the instantaneous description and check whether the Turing machine is calculating that. I'm telling you x equal to 3 and f of x equal to 4. No, x equal to 3. I'm going to find f of x. How will you find f of x? Means initially 3. So 3 zeros are there. I'm going to process. I'm going to check whether the output is correct or not. Initially, how can you write delta of our initial state is Q0. What is our initial string? 0, 0, 0. I am going to calculate this one. 0, 0, 0. So how can I process this one? Means it implies. What is Q0, 0? Q0, Q1, 0, R. So can be written as Q1. I have processed this one 0. This 0. R means now the head is in this position. After processing this one, move one position right. So now it's in this position. So this is the position. Now the next. Again check Q1, 0. What is Q1, 0? Q1, 0, R. So I'll write Q1, 0, R. R means this position. Again Q1, 0. What is Q1, 0? Q1, 0, R. So I'll write Q1, 0, R, 0, 0. This 0 give the 0 as it is and R. Move here. When you move here, you encounter this blank. This is the blank. Nothing is there. No. What is Q1, blank? Q1, blank is Q2, 0, R. It can be written as Q2, 0, R. 0, 0, 0. The blank can be converted into 0 and move the read write head R. Now check whether you reach the final state or not. We already mentioned that Q2 is the final state. So we reached the final state Q2. Hence, this is our answer. Nearer to this one is our answer. So our answer here is 0, 0, 0, 0. What is given? We are given 3 zeros. The answer is 4 zeros. What is our function? F of x equal to x plus 1. If I give 3 zeros, I'll get 4 zeros. So this is the correct. The descriptions are correct. We can draw the transition diagram also for this Turing machine. What is that? Q0 is there. How many states are there? Q0, Q1, another one is Q2. These are the states. So Q0, 0. What is Q0, 0? 0, R. So Q0, 0 means Q1, 0, R. Q0, 0 means Q1, 0, R. 0 means 0 R. Oh, right. Then what is Q1, 0? Q1, 0, R. So Q1, 0 is Q1, 0, R. Write these things here. And what is Q1, blank? Q1, blank means Q2, 0, R. Blank if it reaches blank, 0 R. So this is the transition diagram related to this function. Like that, we can compute anything or calculate anything. Until then, we check the content, but here onwards from the Turing machine, we can check the contents. That is, we will calculate. If x is given, we can calculate x plus 1. Similarly, if a and b values are given, you can calculate a plus b. You can calculate a minus b. So, you can calculate a star b. Hence, the Turing machine can be acts as a calculator. This is one of the computing device, and all the languages or all the recursively enumerable languages are accepted by the Turing machine. Or the language accepted by the Turing machine is called as the recursively enumerable language. That's all. Thank you.